Look at the central void of the Opus in Dubai. The glass flows like liquid across a massive free-form surface. Your first instinct is to assume every curved pane was manufactured in exactly that permanent shape. But that assumption hides a counterintuitive engineering reality. Some of this curved-looking glass actually began its life completely flat. Engineers mechanically deform industrially produced flat panes into different geometries, restraining them against specialized frames. The architectural shape itself creates a permanent state of engineered stress inside the material, long before the building faces wind. Engineers normally spend their careers protecting brittle materials like glass from unnecessary tension. Why deliberately force a flat sheet into a stressed curve before installation? And how far can they bend it before the geometry itself becomes the problem? To understand this challenge, you have to look at the architecture demanding it. The Opus features a central, free-form void carved through the structure. The glass facade, enclosing that void, covers approximately 6,000 square meters, built from roughly 4,300 individual glass units. Those units include a mixture of flat glass, single curved glass, and double curved glazing. When viewed as a single surface, the geometry appears seamless. But beneath that fluidity is a massive mechanical puzzle. How do engineers cover an extreme, unpredictable surface using an industrial material fundamentally produced in rigid, flat sheets? Engineering literature identifies the Opus as a prominent project combining hot bending and cold bending techniques to achieve its final form. This proves the story is not a theoretical design concept, but a fully realized application in a demanding construction environment. To understand why both techniques are necessary, you first have to separate how they interact with the material itself. The difference between the two approaches fundamentally changes what the glass experiences. In traditional hot bending, the glass undergoes significant thermal processing. The material is heated until pliable, formed over a mold, and then carefully cooled. The new, curved geometry becomes the permanent manufactured shape of the pane. It is completely stable in that configuration. Cold bending operates on a completely different mechanical principle. The glass panel arrives on site, or at the assembly facility, effectively flat. It is then mechanically pushed, pulled, or twisted out of its original plane and locked into a curved frame. This process relies entirely on elastic deformation without any thermal reforming. The glass simply bends the way a thin ruler bends when you press down on its edges. It sounds like an elegant shortcut to achieve fluid architecture without the expense of custom manufacturing. But locking a flat pane into a curved shape introduces an immediate physical consequence. What happens if you remove the mechanical force holding the glass against that frame? If you release the restraints on a cold bent panel, it elastically rebounds toward its original planar geometry. That reaction reveals the invisible reality of a cold bent facade. The glass is held in a forced equilibrium configuration. The imposed shape is absolutely not mechanically free. In permanent cold bending, the required geometry creates a constant state of internal stress inside the glass and exerts continuous forces on the supporting structural system. The curve is not simply a visual characteristic that the glass possesses. It is a mechanical demand that the entire facade system is constantly asking the glass to maintain. Technical research into cold-bent structural glazing specifically models this equilibrium state to calculate the maximum stress and the reactionary forces pulling against the interfaces. Engineers must account for the continuous shear, rotation, and tension acting on the structural framing and adhesives over the lifespan of the building. The architectural shape itself comes with a permanent mechanical cost, which leads to the most logical question about this entire practice. If bending flat glass intentionally introduces permanent stress and continuous structural loads, why do engineers agree to do it at all? The answer lies in the shifting demands of modern skyline design. Contemporary architecture increasingly requires building envelopes to follow highly complex, free-form, and double-curved surfaces. Producing thousands of unique, individually hot-formed pieces for a massive skyscraper facade can become incredibly slow, complicated, and expensive. Cold bending offers a highly practical alternative for specific geometric conditions. It allows planar-produced industrial glass to realize some of these complex architectural visions through controlled mechanical deformation. It provides a cost-effective option to navigate the space between flat manufacturing and curved architecture. When applied to the right geometries, it is an undeniable engineering triumph. But the mechanics of elastic deformation do not scale infinitely. If the glass can bend, why not just bend it exactly as far as the architect wants? Cold bending is not simply a matter of pushing an industrial glass panel until it finally fits into a curved aluminum frame. As the imposed deformation increases, everything about the system's mechanical response changes. The internal stress distribution shifts, the reactionary forces escalate, and the final equilibrium shape of the panel evolves. These mechanical reactions depend entirely on specific design variables, including panel dimensions, glass thickness, boundary support conditions, and the required curvature. Research into cold bent glass has identified a critical boundary within this process. Engineers know that in certain structural configurations, adding more imposed deformation does not just increase the internal stress in a steady, linear progression. Instead, the geometry itself can reach a strict physical threshold. When pushed past that threshold, the panel can trigger deformation-induced stability issues. Geometric instability is one possible design phenomenon that facade engineers must actively account for when developing certain cold bending configurations. This creates a massive mechanical problem for the architecture. What happens if adding a little more imposed deformation does not simply create a slightly more curved version of that exact same panel? What happens when the shape itself breaks the rules? Research on cold bent glass reveals exactly what happens when the shape changes the structural rules. Imagine a completely flat, rectangular glass panel. Apply mechanical force to push one single corner out of its original plane, creating an anticlastic or saddle-like deformation. Initially, the glass accommodates this force by forming a smooth, stable, continuously curved surface. But if you continue to drastically increase that imposed deformation, the panel can experience a sudden change in its deformation mode. Research on cold bent glass has found that some configurations can experience buckling or snap-through type geometric instability. It is critical to understand that this phenomenon does not mean the building collapses. It does not necessarily mean the glass immediately fractures or shatters upon installation. In some cases, geometric instability may first become a severe serviceability, optical, or design acceptability problem. The reflection across the surface becomes heavily distorted, the geometry breaks its intended fluidity, and the mechanical behavior fundamentally shifts away from the architect's vision. Other conditions and combined loads can create far more serious structural concerns. The most important engineering takeaway is that there can be a distinct point where asking for more bend is no longer simply asking for more of the same. The shape itself reaches a limit. This phenomenon is exactly why facade engineers do not manually force materials into shapes on a construction site and merely hope the glass survives. Cold bent facade design uses highly advanced numerical modeling and complex finite element analysis. Long before a single pane is manufactured, computational cold bending research allows engineers to predict the panel's deformed equilibrium shape with incredible precision. They map the maximum stress points, model the reactionary forces, and conduct rigorous stability analysis to find the exact threshold of geometric buckling where relevant. Modern analytical methods can provide real-time feedback on stress behavior while the proposed geometry is actively being changed in the software. The building does not simply force the material to obey the architecture. Architecture and mechanics have to negotiate. Engineers use this data to ensure the design stays safely away from unacceptable configurations. But cold bending is not necessarily the only load the installed panel will ever experience. Technical facade analysis treats permanent cold bending as a long-term imposed condition. The internal stress and the forces pulling against the structural frame operate as a continuous mechanical baseline. But the building also exists in a highly dynamic physical environment. Engineers must consider short-term design loads, such as intense wind pressure or suction pulling at the exterior of the skyscraper. When a massive gust of wind hits the tower, the cold bent panel does not get to return to a flat, relaxed state to handle the impact. It must absorb that dynamic environmental force while already being held in a permanent state of engineered deformation. The architectural shape is load case number 1. The building's environment is load case number 2. The physical shape is not just a visual feature, it is already a structural load that the panel has to carry. When you combine the imposed deformation with external environmental loads, the definition of pushing a material too far becomes highly specific. Asking for too much curvature does not automatically mean the glass explodes. Depending on the geometry and the edge support system, the design concerns usually trigger long before any cinematic disaster occurs. A proposed shape might create excessive tensile stress that reduces the material's safety margins to an unacceptable level. It might cause severe optical distortion or approach the boundaries of geometric instability and mode change. It can also place extreme long-term shear forces, tension, and edge rotation demands on the structural silicone interfaces holding the panel to the aluminum frame. The engineering problem is simply that the proposed geometry can leave the acceptable, calculated design space. A facade does not have to collapse for a curve to become mechanically unacceptable. It only has to exceed the safe operational limits of the system. Understanding that absolute physical boundary brings the story directly back to the opus. Because when you look closely at its structure, you realize the engineers made a very specific choice. Return your attention to the central void facade of the opus. You are looking at approximately 6,000 square meters of glass, relying on roughly 4,300 individual glass units. At the beginning of this investigation, you saw a seemingly effortless, fluid glass surface. Now you understand that the facade is divided into thousands of individual geometries, each with its own mechanical demand. The opus includes flat glass, single curved glass, and double curved glazing. Engineering literature identifies this specific free-form project as using a coordinated combination of hot bending and cold bending techniques. This is a major revelation about how extreme skyscrapers are actually built. The architecture does not rely on one single universal bending trick to cover its entire surface. Different zones of the geometry create vastly different mechanical demands on the material. Not all 4,300 units are cold bent. Not all double-curved pieces are cold bent. The project uses a strategic combination of bending and glazing strategies across a highly complex facade, which finally answers one of the longest-running questions about this entire structural process. If cold bending is such a practical, cost-effective way to achieve curved architecture, why not simply cold bend every single pane on the building? Why introduce the immense expense of hot forming if cold bending can achieve the same visual result? Because physics demands a compromise. The simple answer is that cold bending has absolute physical limits. Technical facade documentation for the Dubai Freeform project explains exactly how this boundary is handled in reality. Engineers specifically deployed traditionally hot bent glass in the areas of the facade, requiring extremely high curvature. They did this because those specific geometric zones would have completely exceeded the acceptable mechanical limits of cold bending. This is the clearest possible demonstration of a fundamental structural rule. The material can mechanically say no to the architecture. Some moderate geometries can be achieved safely and efficiently through controlled elastic deformation. Other, more extreme zones absolutely require a permanently hot-formed geometry to survive the building's service lifespan. These two methods are not competitors, where one is inherently good and the other is bad. They are simply different engineering tools deployed for vastly different geometric demands. The architect has the freedom to draw almost any fluid curve on a digital screen. The glass simply does not promise to reach every single curve in the exact same way. When a curve becomes too aggressive, the strategy must shift. But what happens when hot bending is not an option? What happens when a proposed cold bent shape pushes the glass into geometric instability, but hot forming is simply too expensive or impractical for the project. The engineering solution is not always to force a stronger, thicker piece of glass into the frame. Cold bent facade design actually makes the building's geometry itself part of the engineering optimization process. Research on computational cold bent facades demonstrates advanced methods where designers can actively modify a proposed parametric surface while receiving constant mechanical feedback. They receive real-time data on the panel shape, the exact deformation mode, and the maximum stress levels. The design can then be carefully refined to keep those stresses within absolutely acceptable limits. Engineers can alter potential variables, including the panel boundaries, the severity of the curvature, the panelization strategy, and the structural support geometry. This creates the most powerful engineering revelation about modern skyscraper construction. Sometimes the ultimate solution isn't stronger glass. It's a slightly different curve. The structural engineer is not merely checking the architect's finished drawing to make sure the glass survives the wind. Engineering actually helps determine what architecture is physically reasonable in the first place. It is a continuous negotiation between the desired aesthetic and the strict laws of material mechanics. The final shape is not just an artistic choice, it is an optimized structural compromise. To understand how this negotiation works in practice, you can picture the panel's capacity as a mechanical stress budget. This is not an official engineering term, but it is the perfect mental model for how the system operates. The curved architectural geometry already imposes an engineered stress condition on the glass. That means a portion of the material's structural capacity is spent just holding its shape. Other design loads still have to be considered and safely absorbed. Therefore, engineers need to understand exactly how much demand comes from the imposed curvature, the rigid supports, and the physical glass dimensions. They have to calculate how much of the budget is left for wind pressure and other service loads. The conceptual takeaway is incredibly simple. The shape itself consumes part of the available mechanical design space. And that realization leads directly to the most profound intellectual shift in how we view these massive glass towers. Stress is no longer an invisible enemy that must be eliminated at all costs. It is a quantifiable resource that must be managed. At the beginning of this story, you likely assumed that stress inside a brittle material meant something had gone terribly wrong. We naturally associate stress in glass with imminent failure or catastrophic structural collapse. But in the highly specialized field of cold bent facades, that assumption is entirely incorrect. Intentional, elastic deformation and the associated stress can be an active, calculated part of the design concept. Therefore, achieving absolutely zero stress inside the glass is not the objective. The true objective is a highly controlled, strictly calculated, and mechanically acceptable response. Research on computational cold bent facade design explicitly focuses on keeping those occurring stresses safely within the acceptable limits of the glass. Architecture desperately wants absolute fluidity. Glass demands strict physical rules. Engineering simply creates a highly negotiated space between them. The remarkable part is not that engineers somehow magically remove stress from the glass. It is that they know exactly how much deformation the design can ask for, and precisely where to stop asking. They map the boundaries of failure, and safely build right up to the edge of the acceptable zone. Stress is not the enemy. Uncontrolled stress is the enemy. Look one more time at the completely flat, rigid industrial pane of glass from the very beginning of this story. Now look back at the sweeping geometry of the Opus, or the 83 soaring floors of Ocean Heights. At the start, you likely only saw curved facades. Now, you see manufactured flat sheets, imposed geometries, strict bending limits, and calculated equilibrium shapes. You see the intense computational analysis and the strategic panelization required to hold those shapes in place. This does not imply that every single curved facade in Dubai is mechanically cold bent. It does not imply that every single curved pane in the Opus began flat. The correct takeaway is far more specific. Cold bending is one highly calibrated engineering method among several used to realize complex glazed architecture. It is a tool that transforms a standard industrial product into a custom architectural feature. But it only works if you respect the math. When you finally view these towers through the lens of mechanical deformation, the visual architecture feels completely different. The building looks entirely fluid. The material covering it remains inherently brittle. That massive physical contradiction only exists because the geometry, the material behavior, the fabrication, the panelization, the supports, the bending strategy, and the stress analysis were flawlessly coordinated. Some of Dubai's most fluid-looking glass architecture is only possible because engineers know exactly how much a brittle material can be asked to bend, and they know exactly when to stop asking. They know how the panel deforms, how the internal stress changes, and where the geometry becomes mechanically unacceptable. They know when cold bending is appropriate, when another fabrication method is absolutely needed, and when the architecture itself should be modified to satisfy physics. The success of these structures proves that intentional stress is not a failure, but a calculated variable kept strictly inside an acceptable mechanical envelope. The final image is a testament to that invisible calculation. The curve looks effortless. The calculation holding it there isn't. Some of Dubai's complex glazed facades use cold bending to mechanically deform initially flat glass into curved installed geometries. That deliberate deformation creates a real engineering stress state with practical stability and load limits. This reality forces facade engineers to meticulously model the glass, choose precisely between cold and hot bending strategies, and sometimes adjust the architecture itself. The ultimate goal is to ensure the desired curve remains safely inside an acceptable mechanical design space, proving that controlled stress is a foundation of modern design. This video is for educational and analytical purposes, based on publicly available engineering research and facade design literature. It does not represent a structural diagnosis of any specific building, nor does it imply the imminent failure of any cited project. If you want to understand the invisible mechanical rules governing the world's most ambitious architecture, leave a comment below with your thoughts. Make sure to subscribe to Dubai Viral for more investigations into the engineering systems shaping the modern skyline.